talk. It's by Jacques Franchi, and he will talk about hyperbolic geometry from the point of view of Minkowski space and the Lorentz group.
I give you now the structure of the elements of the Lorentz group. There are three categories. Each element of PSO1D is of one of the three following types, and only one. First category, those elements with a time-like eigenvector are conjugate to an element of the rotation group, subgroup SOD. Of course, these are called the rotations or elliptic elements. Those without time-like eigenvector, but with two distinct like eigenvectors. Are conjugate to an element having the following form: hyperbolic cosine, hyperbolic sine, and so on. And here some rotation with R in R and big R in SO D-1. This is actually elements of PSO11 product with SO D-1. This is the generic element of this particular subgroup, actually. And this one are called the boosts. We only saw this morning a particular subcategory of those. Or also loxodromic. They are also called loxodromic elements. And the third category are made of those without time-like eigenvector and a unique right-like eigenvector. They are conjugate to an element the following form: 1 plus u squared over 2 minus u squared over 2 plus u squared over 2, 1 minus, and then u minus u 1 note rho rho with rho in SO d minus 2. These are the elements of the form theta plus u e 2 times rho, commuting, of course. And u is any real. This is a subgroup of type T1 with my notation of this morning times SO d minus 2. These are called parabolic elements. My horizontal translations of this morning belong to this class. Remarks or corollary of this structure result. First, all eigenvalues belong to R plus star, strictly positive reals, or to the unit circle of any isometry of Minkowski space. For any isometry, you can have only positive eigenvalues or eigenvalues with modulus 1. And another moral of that is that non-trivial boosts form a dense open subset in ASO1D. So the main category is the second one, the boosts. They are dense in PSO1D. The reason is very simple. With this decomposition, it is easy to verify that all the other ones have the eigenvalue 1. So one can think of the Lorentz-Möbius group of being made essentially of boosts. When D is equal to 2, it is very simple to verify that these three categories are in bijection with the size of the trace of the matrix, equal to 2 or less than 2 or more than 2. Now, hyperbolic space and its boundary definition. Definition is very simple. I only take to be HD the half pseudosphere of Minkowski space. Those C in Minkowski space which have one pseudonorm and take only the positive upper sheet. So you have the light cone. Here is node, and I take this upper sheet of hyperbolic. Only the upper sheet. This is HD. This is, of course, also the set of vectors that can be written hyperbolic cosine of R times E naught. E naught is this unit vector plus hyperbolic sine of another one, I denote by U, with R inter plus and U in S B minus 1. It is, of course, preserved by the Lorentz modulus group. And by subgroup, affine subgroup acts transitively and properly thereon. So AD acts on HD. So transitively and properly, this means that for any P in HD, there exists only T X, Y belonging to the affine subgroup, such that the image of the first canonical vector is precisely P. So these two elements are called the Poincaré coordinates. Of P. And it will be often very convenient to see the whole thing in the space of Poincaré coordinates. And they are immediately computed, since I've written, displayed expressions for the matrices, the two matrices coming into this notation here. And so I have only to perform a product of two matrices as I wrote this morning, and I get immediately this expression over 2y is 0 plus this with a minus 1 e1 and some for j going from 2 to d of xj over y ej. And in the reverse direction, equivalently, the coordinates are easily computed like that. This is merely 1 over the product of P with E0 plus E1 and the other coordinates in a similar way are written like that. This is minus PEG over E0 plus E1. So it is easy to perform the computation. This is got merely by solving this. Then I introduce light rays as the boundary. A light ray will be future directed like direction. So like this one here, or this one here, you see two light rays. So these are the half lines, upper half lines of the light cone, and the boundary of the hyperbolic space will be the set of these light rays. This is then the light cone confronted by dilatations by elements in R+. So R plus psi or R plus star with psi in the light cone. So it identifies with the boundary of HD in the projective space, in the projective Minkowski space. So this is a natural identification. This is very natural at the level of the projective space. Just a little remark. For any theta in this boundary, eta orthogonal, the orthogonal of eta is the hyperplane tangent to the light cone and containing eta itself, since eta is light-like. This is the unique hyperplane tangent to the light cone C and containing the same eta.
In the definition of delta HD, what is that reason they say it is the whole light cone? No. Should be just a future reactor?
This is the whole half-line here.
Yes, but where C should be a future directed light direction.
Yes, see, this was the light cone. See, I introduced this morning. This is the light cone. This is a set of vector C, which have pseudo-norm null, and the first coordinate is positive. Now we have two important decompositions. They are simple to state and to establish, but they play an important role. The first one is the so-called carton decomposition. Any element gamma in the Lorentz group can be written as gamma equal to, I noted by rho, theta r, rho prime, with rho prime in SOD, and real, positive real, but to take it positive. But this is not only that, moreover, we have are uniquely determined by the following feature. R is equal to the logarithm of the Euclidean operator norm of gamma. Here is Euclidean operator norm of the matrix gamma. And this is the same as the norm of its inverse element. It happens to be the same. So gamma, this is the maximum of gamma V over V with V in SD, and here Euclidean norm. And there is not exactly uniqueness in this decomposition because you can modify rho by some rotation in SOD minus 1. SOD minus 1, I already mentioned that it is commuting with this boost here. So this writing is not exactly unique. It is, however, useful. Now I come to the second one, which enjoys uniqueness. So, second important decomposition is Iwasawa decomposition. Of course, these two decompositions occur in much more general Lie groups than the Lorentz group, but for each of them it is an important feature. So this decomposition is as follows. Any element in place O1G can be uniquely, this time, written as gamma is Txy rho with Txy in the half-time subgroup and rho in SOD. And I recall this, the meaning of this is theta plus x, theta log logarithm of y, rho. Well, this is very simple. You can get this immediately. You have only to choose as y and x to be the point carré coordinate of gamma of the first canonical basis vector, gamma E naught, and so you have gamma E naught equal t x y E naught, and you have only to take rho to be the inverse of that multiplied by that, and by definition it preserves E naught, and so it belongs to this one. This is the definition of this one. And uniqueness is no longer, no more difficult. Now, I introduce the hyperbolic metric. It will be easily given by the Cartan decomposition, makes the links between hyperbolic space and Cartan decomposition. Then I'm speaking now from the hyperbolic metric. Proposition. Given P and P prime in HD, two frames beta and beta prime, such that P is the first vector of the first frame, and P prime of the second one. The size are equal to the logarithm of, I take in this sense, I take the same thing as in the Cartan decomposition I just raised. You take here the only element of the Lorentz Möbius group, which is mapping the canonical base onto this frame. And the same here, and you take this thing, and the operator norm is the Euclidean sense, as I specified just before. And this I denote by distance between P and P prime. Of beta, I finish my phrase, of this element in the Cartan decomposition, and its Cartan decomposition. Depends only on P and P prime. Moreover, we have an easy expression for that. Moreover, we have merely distance between P and P prime is the inverse hyperbolic cosine, maybe not like that, of P prime product. So I have two vectors in my hyperbolic space, in my upper sheet of hyperboloid. I take their Minkowski or Lorentz product, pseudo norm, and the inverse, this is also denoted by that. This is the same. So I have a very simple expression actually for this distance.
Sorry, what do you mean by this notation? P equals B0.
Because that frame beta in FD, this means that beta is a frame, so it has a first vector, a second vector, and so on. And this one has to belong to HD.
Okay. So it's the first vector.
The first vector only. Maybe I can write the beginning or an abbreviated proof for that, because I'm saying from the beginning that all computations are simple. Maybe I prove it at least once. But it is not at all difficult. This is basically a linear algebra. So it cannot be very difficult. So I'm writing the Cartan decomposition. So I have this with some decomposition like that. And if I add another one, gamma naught equal to P, if I have another representation for these two vectors in HD, like that, then I will have see, you consider simply gamma minus 1 beta, and it will necessarily preserve the first vector E naught, so it will be a rotation in SOD, and the same for the other one, for the same reason. And so you will have only to write this one prime, I have prime here. Only you have to replace using this. You will have merely this thing and rho prime beta tilde prime minus 1 gamma tilde prime with two rotations. So R will be the same, directly, straightforwardly. Then you have this formula with what I have written before in the Cartan decomposition. And you see on this expression that triangle inequality will be almost obvious. You have just to compose two things like that. This is almost obvious. This is straightforward to get the triangle inequality from this expression. And you have also clearly R equal to 0, equivalent to saying that this thing here, this isometry belongs to SOD. And this is clearly the same as saying that P is P prime. This is also straightforward. And finally, if I want to make this formula more obvious, have only to consider so the distance between P and P prime. This is the distance between beta tilde E naught, beta tilde prime E naught. This is as above, and this is the same as my expression here for I am beginning with the right hand side. It is more simple. So I write, this is this thing, and since this is an isometry, I can put it on the other side. So I'm getting E naught, this, and now I am using once again this decomposition. The rotation parts will preserve E naught, so they disappear. So this is the same thing as the inverse hyperbolic cosine of E naught, theta r E naught, and this is obvious on the seeing the matrix theta r with this hyperbolic cosine, that this is merely r. So this is very direct, straightforward. Then, to be confident, it is also not difficult to establish, to verify that the whole isometry group is realized by means of the Lorentz modulus group. So we get in this way the whole isometry group. Of orientation preserving isometries then of HD with this distance. So usually this isometry group is called the modulus group, and this is hence the same as the Lorentz group. They are isomorphic. Now I can deduce a more general expression for hyperbolic distance, but not that much. The hyperbolic distance not more general, but in the point carré coordinates between Q1 and Q2 in the hyperbolic space, having point carré coordinates. So I'm just expressing the hyperbolic distance in terms of point carré coordinates. X1, Y1, and X2, Y2, respectively, can be expressed by distance between Q1 and Q2. So recall this is my inverse hyperbolic cosine of the pairing between both. And this is easily written with these coordinates. This is the square of the difference between these two vectors of R, this is Euclidean distance in R to the d minus 1, plus the sum of squares of the y's over 2 the product. And once again, the proof is very straightforward. This is only due to the expression of the entries of the matrix I displayed before. So I have only to take this. I have only to perform this product, and this is very easily seen since I can once again map this one on the other side, taking its inverse. And I wrote this morning as the last one, the formula giving the product in this affine group. So it is only x1 minus x2 over y1 and y1 y2 over y1 and E naught. And so you just have to consider the first entry up and left of this matrix, and it is giving directly this. As a corollary, I can mention that the Riemannian way of thinking of Riemannian distance is easily recovered from that very directly. So, writing the distance between some element of the hyperbolic space and perturbation of it by, say, small delta, small vector delta, and a small real epsilon, say, and writing the above expression, I shall have 1 plus beta square plus epsilon square over 2y plus epsilon. And of course, this is equivalent to square root of delta square plus epsilon square over y. So this is the usual expression for the Riemannian hyperbolic metric. So this is a direct consequence, of course. Now, I go to geodesics and light rays, their connection with light rays. By definition, a geodesic will be the non-empty intersection of the hyperbolic space with any vector plane of the Minkowski space. So geometrically, this is a very simple thing. I have only to cut by some plane here and the trace of the plane on the hyperbolic space. This is my geodesy. Something like that. Only the traces of the vector planes on the hyperbolic space. Remarque, for any, there is a unique geodesic containing any distinct points, any two distinct points of HD or its boundary. If I am taking an edge of the light cone, this goes as well as when I'm taking two points within the hyperbolic space. This is not more complicated. I have some time left, or
2 minutes.
2 minutes? So just one proposition. I will state a proposition stating and specifying how to project onto a light ray for any P and eta belonging to HD and to its boundary respectively. It exists a unique P eta and xp belonging to Minkowski space times eta such that I have P eta orthogonal, P eta as -1 pseudonorm, and P plus P eta equals eta B. This is easily understood on the picture. Here the light ray eta, here is low, here is P, is P orthogonal, and I have a unique way of decomposing like that. Here is P eta, and here eta P. And the interest of that, one interest of that, is that it is linked with the tangent bundle of the hyperbolic space in this way. This is precisely the set of elements, line elements, like that, belonging to HD times F1D, such that Q belongs to P orthogonal, and Q equals -1. This is the unique tangent bundle. And as I already mentioned, FD is the frame, actually the frame bundle of the hyperbolic space. This decomposition is very easy to get. Only not the proof, but only the result is interesting. So I finish with the remark that you get the hyperbolic space as the quotient under the right action of this rotation subgroup of the set of frames, and in a similar way, if I am quotienting only by SO d-1, I recover this one up to an identification. Actually, I get more precisely this, but this is very, very much linked. So maybe I finished there. Thank you.